Hello everyone. For me, it's a pleasure to stay here today. My name is Juan José Jimenez from Fria. I am Associate Professor of the Mechanical Engineer Department of the Pontificia Universidad Católica del Perú. Today, I will present the work titled Resistance Prediction of Laminated, Fillet-welded, and Full Penetration-welded bolted T-stub connection, where I will show the first results of a more extensive research that we are performing at this moment. I have divided the presentation into the next parts. First, I will explain the theoretical background and the objectives of the study. Then, I will describe the works performed to reach these objectives. After, I will explain the methodology in terms of procedures and techniques considered, as well as the results. Finally, I will exhibit the conclusion obtained from results. The component approach considered in Eurocode provisions assumes any joint as a set of individual basic components, characterized by their mechanical properties of strength, stiffness, and ductility, depending on the position and the geometry. In the particular case of bolted moment and plied connection, the T-stub is the component which mainly controls the behavior of the tension zone. This component is defined by two symmetric T-profiles connected through their flanges by bolts and submitted to tension loads in the webs until rupture. The Eurocode analytical model is obtained by the application of the kinematic method, considering an equivalential rectangular cross-section with a possible collapse pattern and obtaining the ultimate loads by the application of the virtual work principle. According to the geometry and the mechanical properties of the T-profile and the bolts, three different mechanisms of failure can be reached, depending if the failure reached is as a consequence of the yielding of the flange, the rupture of the bolts, or the plastification of the flange and the bolts simultaneously. The objective of this work is to analyze the influence of the wet-to-flange connection type in T-stub components with two different techniques, experimentally and numerically by finite element simulations. The welding topology influence of the distance from the bolt axis to the midspan of the equivalent analytical beam. So, as the bending is governing effect, it is important to study. The analysis has been performed by two different methods, experimental and by finite element simulation. The same geometry was tested with three different wet-to-flame connections, one continuously, one fillet-welded, and one groove-welded. In the case of the experimental works, two specimens of each topology were tested. Tests were performed in a universal testing machine. Specimens are symmetric, so only a half bolted and supported to a stiff part can be tested. A rigid base was manufactured where each T-profile was bolted and tensioned. The data registered in each test is the load applied and the displacement of the moving cruise head. Additionally, during the test, the displacement of aleatory distribute points marked on the front surface were recorded, and finally the displacement and strain fields obtained by the digital image correlation approach. Non-linear behavior, force displacement of a specimen, was registered and graphically represented as illustrated. The force corresponds with the measured by the testing machine, and the displacement is the double of range midpoint calculated value optically. So possible slipping are avoided. In results, characteristics force displacement relationship of ductile connections were observed. For the first stage is observed a linear elastic behavior. As the load increased, the bolt and the flange start yielding, so begin to reduce the stiffness until the rupture of some of the elements, the bolt or the fracture in the welding too. Additional to the T-stub results, mechanical properties of flange and bolt steels were characterized by tension tests in coupons obtained from the same plate used to manufacture the specimens and machining additional similar bolts. This data is necessary for the numerical simulation of the theoretic analytical values calculated. Three parametric models were programmed with the same geometrical properties that specimens tested. 1/4 of the T-profile because of the double symmetry, and the bolt were modeled with three-dimensional 8-node brick elements, considering geometrical and material elastoplastic non-linearity with isotropic strength hardening, and the von Mises yield criterion. The base was also modeled, and joint elements were considered to simulate the iteration between parts when the tension load is gradually applied from zero to the end of the simulation. Proper boundary conditions were considered to define the symmetry of the model. The model was calibrated with experimental tests performed by comparison of the force displacement curves and also checking mesh convergence. Figures below show finite element results represented simultaneously with experimental. Both curves show also the non-linear behavior. Finally, experimental and simulation curves were represented simultaneously, and is observed a good correlation. The following conclusion can be drawn from the works presented above. The strength of the continuous T-stub is the highest. This fact is produced because the value of the M factor is the lowest, and because the influence of the fillet radius between the web and the flange, which avoid stress concentration in the material. On the other hand, the difference appreciated between welded T-stub is very small. According to the initial stiffness, the highest reached was in the groove welded specimens, but it is observed that two stages can be observed until the complete yielding. Finally, I want to thank the Pontificia Universidad Católica del Perú, Dirección General de Investigación for financing, and CITE Materiales Laboratory for the facilities for the execution of the test. Also, is appreciated the donation of material by the steelwork contractor S-Metal. Thank you very much for your attention.